So with that, let's now go on to the noise margin analysis. So the ideal voltage transfer characteristic was like this, right? A very sharp thing at around VDD by 2. Not necessarily, I can actually move that little bit here there depending on my threshold that I need, right? The trip point would be at VDD by 2, okay? So this is VDD. So it's very clear that V in, if it is less than, let me call this as the trip point Vm. Vn less than Vm implies V in is logic 0, implies V out is logic 1. If V in is greater than Vm, right, implies V in is logic 1 and this implies V out is logic 0. No problem here in the ideal case, okay. Now I want to see how does this analysis work for the real inverter, because there is a deviation from this ideality. So if you consider the VTC of the real inverter, it would be slightly exaggerated, I am showing, but yeah, this is my Vm, right. Clearly this definition does not hold here. If V in is greater than Vm, it doesn't mean that it's a logic 1. Neither is it true that if V in is less than Vm in the real inverter, that the input can be treated as a logic 0, okay. So there is some region before Vm somewhere, I don't know where this is, we are going to pin it down in this discussion today, right. Anything to the right of this line can be treated as logic 1 for input for the V in. Anything to the left of this line can be treated as logic 0 for V in, okay, and of course this is V out versus V in, okay. So now let's go back to the, I am just going to draw the inverter like with a schematic symbol like this, fine. So I have an input like this, the output will also go something like this, right, and maybe if I have to draw it, there is a delay and all that, so it would be like this, fine. So in steady state, my input is fixed at either 0 or logic 1, okay. In reality, in a chip, it's not true that the signal will be so ideal, okay. So therefore, I am going to constantly have some noise perturbation around this, okay. And a robust inverter is one which is immune to this noise in steady state. Of course, in the transient region, that's a different case. You know, anyway, there is a transition, some noise here, there. We can't do too much there. But in steady state, any noise, the inverter must be immune to it, which means that the noise must get killed. Okay. So what does it mean to say that the noise must get killed? So let us look at 3 regions, okay, region 1, 2 and 3. To the right of some point, I am going to analyze what happens if there is noise, okay. So this will determine where our boundary should be, where this region 1, to region 2 transition happen and 2 to 3 transition will happen. Suppose there is noise now, if my input is very close to 0 here, let's say I have a noise like this. What will happen to this noise at the output? Huh? Why? Sorry? What does that statement mean? More precisely, more mathematically, what does that statement? You are right. Whatever you do, we are getting the same output. What does that mean again? Mathematically, what does it mean? V out. So delta V out by delta V in is 0. That means the derivative is 0, which means the gain at that point is basically 0. Right? So if you look at this point here, dV out by dV in is 0. Right? Which means that the gain is 0. So what it means is that if there is noise, the noise is getting killed because it does not getting amplified. In fact, it's getting attenuated and it's all gone. So the noise fluctuation at the input cannot percolate to the output. Right? Similarly, in region 3, I can do the same analysis. I have a noise perturbation. Very clearly, here also dV out by dV in is 0. Again the gain is okay. Now what happens if I do the same thing in region 2? Here, I am going to do the same thing here. I will pull this thing here. I have a noise. Okay, or let me just maybe make it like a sinusoid. What will happen to the output here around Vm? Huh? Sorry? Amplified, because the gain in this region is extremely high. It's actually, it should be a vertical line. Gain should be infinity there. But since there is a deviation, it's slightly, this thing, it has a very large gain in this region, which means the output will actually get inverted and it will appear like this. Right? But of course, it's not like, it can be a sinusoidal like this, because as I move away, the gain is changing and all that. So effectively, it will be a distorted, sine wave. Right? So the point is, as I am moving from left to right, my gain is going through some changes. Right? And if you adopt this definition that noise should just get killed in order for the inverter to be robust, then the region of transition where below some level it is treated as logic 0 and above some level it is treated as logic 1, what should be the transition value for the gain when I go from region 1 to 2, 2 to 3? What do you think this magic number for the gain should be? Here gain is 0, here gain is 0, here gain is very high and it is a negative number. Okay, it is gain, mod gain is actually much greater than 0. Okay. So what do you think should be this magic transition value for the gain for me to determine these regions? Noise should not get amplified. That means the region, the point at which the gain actually hits -1 is the point to the left of which gain noise gets attenuated, to the right of which noise gets amplified for coming for the low level. For the high level, right of that noise gets attenuated, left of it noise gets amplified. Therefore, the region of importance is really when gain equal to -1, that is dV out by dV in equal to -1. Right? Because any small value, if the gain goes slightly above that, then the noise is getting amplified. The least or the limiting case is noise does not get amplified, it just goes through as it is. At least you're still okay, because assuming that the noise is of reasonable value, it goes through to the output fine, it's not going to affect the next inverter too much. But if it gets amplified, then you have a problem. Okay, any questions here? Yeah, correct. So when we say noise, it means that it's a reasonably small signal. If you have like a VDD noise, then that's not noise, that's signal, right? So it does depend on the magnitude, but the assumption is it is reasonably small. Okay, and that can sort of, it's okay if it goes through unamplified or attenuated, no problem. Okay, why? Because now if I have another inverter here, I have noise from here, it goes unamplified here, then the same thing will continue in this cascading thing. Now if the noise comes here and then gets amplified, then the following stages will have a problem. That's why we are saying that as long as it doesn't get amplified or gets attenuated, there is really no problem. That is my region that I am really going to be worried about, and that is what is going to define what can be treated as a logic 0 for sure, what can be treated as a logic 1 for sure. Okay. So now let me just go ahead and just redraw this so that it becomes easy to. So there is some point where the slope is basically -1. G equals -1. Okay. Now I extrapolate this onto both axes and find the intercepts. The first point I am going to call VIL. This is V out versus V in. This point I am going to call as VIH. Okay. So what does this mean now? If V in is greater than VIH, implies input is logic 0, I mean logic 1. Okay. Now V in is less than VIL, implies input is logic 0, right? Now what happens if V in is between VIL and VIH? Huh? So if the input lands up in this region, it doesn't mean that the output will be stuck. For example, if the input is here, doesn't mean that the output will be stuck here, because at all times in your chip there is noise. There is some noise which is perturbing the all wires, some small noise that will get amplified, and eventually depending on the polarity of the noise, the logic will switch to 0 or 1. There is no question about that. It will never remain there. Okay, because the gain, remember, is extremely high in this region. Even a small perturbation can switch it to logic high or logic low. The problem is it depends on the polarity of the noise. So sometimes it can go to logic 1, sometimes it can go to logic 0, and therefore this is an indeterminate region. If my input lands up here, implies V out will be logic 0 or 1 depending on noise. Okay, because the gain is very high. Clear? Okay, so keep this in mind. Only above VIH it makes sense, below VIL it makes sense. Okay, so these corresponding Y intercepts, right, are my output VOL and VOH. Okay, so VOL is actually very close to 0, VOH is very close to VDD. Okay, but VIL and VIH are not like that. That's actually very close to VDD by 2. Somewhere around VDD by 2, this change is going to happen, right?